Hello. So what I'm going to do in this video is talk a little bit about acids and bases. This is chapter 16. The first topic will be conjugate acids and conjugate bases, but let's do a quick little discussion of acids and bases, and then we'll go from there. So there are different definitions of acids and bases, interestingly enough, and the one that we use actually tends to depend on what the context is. So the one that you may be most familiar with is called the Arrhenius definition. It's actually the same name as the Arrhenius constant in activation energy and kinetics, same person. And the idea is that it's the ionic theory of acids and bases, which is that essentially when you take an acid and you put it into liquid water, you form hydrogen ions and chloride ions. The main point is that you get this, what's called the hydrogen ion. Okay, which is sometimes referred to as a proton, because remember, a hydrogen atom, in general, a hydrogen atom only has one proton, one electron. So if it's a hydrogen ion, you've lost that electron and you're left with a simple proton. So it's called a proton often. Okay. So that's essentially the idea of an acid, is that you form the hydrogen ion when you dissolve it into water. And the base, the idea of an Arrhenius base, is similar. You take some compound, dissolve it into water, and you get another type of ion called the hydroxide ion. Okay, sometimes we write it this way, OH negative. Organic chemists will often write it as negative OH, because the negative charge is really on the oxygen, not on the hydrogen. But this is the more standard way of doing it, at least for this course. This is called the hydroxide ion. Okay, and the reason that we have this concern about acids and bases is that there's a very important reaction, which is the hydrogen ion combines with the hydroxide ion to form water. And this is a very important biological reaction. Okay, so hydrogen ion, hydroxide ion forms water. That's the Arrhenius theory, ionic theory. But we also have what's called the Bronsted Lowry model. And this is actually very often more useful for us. It was developed after Arrhenius had done his work by a couple of different people. And essentially what they figured out was that you can also look at it at an acid-base reaction in the following way. If we observe what happens when we put hydrochloric acid into water, what we find is it donates an H plus to the water, leaving us with chloride ions dissolved in the water. And we get this new species, which is called the hydronium ion. Okay, so this is a different way of looking at acids. Instead of just looking at it as something that produces a hydrogen ion, we're looking at it as something that does something, a reactivity. So what we do is we have these definitions, or we have these labels. We're going to label everything in this reaction. We're going to call this a Bronsted acid. Why? Because it's the one that's donating the H plus ion to the water. This we're going to call a Bronsted base, because it's accepting or absorbing the hydrogen ion. The transfer of the hydrogen ion is to the water molecule. Then what we're going to do is we're going to come up with what we call acid conjugate pairs. So what you do is you identify your acid. So there's your acid. And identify what's left after the H plus is gone, right? So if you take the H plus off of the HCl, you get Cl minus. And we're going to call this the conjugate base. Okay, so these two go together, the acid and the base. If it's on the product side, we're going to call them conjugates. And likewise, see how the water differs from the hydronium by an H plus. That's the only difference is the H plus. So we're going to call this one a conjugate acid. Okay, so the conjugates are on the product side. Notice it's conjugate here, conjugate here. One's an acid, one's a base. The way you tell is you first identify which one's the acid on the left side, on the reactant side. You identify which one is donating the H plus. And you should be able to predict that, right? We know HCl is an acid, so we know it's going to be the proton donor, the hydrogen ion donor. That's our definition of the acid. Water then is the only other thing in there. So it's going to absorb the H plus. It'll be transferred to it. And so we're going to call that the Bronsted base. The Bronsted acid and the conjugate base differ by an H plus. The Bronsted base and the conjugate acid differ by an H plus. So here's our pairs. HCl, and I'll put a line like a slash Cl minus. There's one of the pairs. And then the other one is H2O and H3O plus. By the way, this is called the hydronium ion. And that's essentially another way of representing the hydrogen ion, although it's probably a little more accurate. Okay, so that's called the Bronsted Lowry model. Now let's take a look at an example. So if we take a look here, we've got acid conjugate base. So there's 3 acids that are given. We want to find the conjugate base. And remember, the acid and the conjugate base, it just differs by an H plus. The acid will have 1 extra H plus, or another way of looking at it, the conjugate base will have 1 fewer H plus. So you just have to take the H plus off of it, okay? So for the HCl, if you take the H plus off of the Cl minus, you take the H plus off of this one, which is called bisulfate, you take the H plus off of the water. Now, the base, and see how it's base and conjugate acid? It's the conjugate acid and the base. They differ by an H plus, but the base will have fewer H pluses. The acid will have more. So we're going to add H pluses to these bases to get their conjugate acids. So let's take a look. Okay, so here's our acids. HCl, HSO4 minus, and you can get some pretty exotic looking species and figure out what their conjugates are. These ones are pretty regular, but you can do some pretty exotic species. So again, the conjugate base, you just take off the H plus. So if you take an H plus off, you get a Cl minus, right? Remember, the H plus and the Cl minus, the charges have to add up to whatever the charge of the HCl is, which is 0. Again, take off your H plus. That's going to make this even more negative. So it's actually going to be 2 negative, right? Because you just do the arithmetic. If something is negative and you lose a plus, you become even more negative. So now it's -2. The H plus off of the water, you're just going to have still 1 H and an O, but now you'll have a negative charge. So you're going to have a negative charge. So you could write it that way. I'm not sure that Alex will want you to write it that way, but we could do it that way in there. You have your hydroxide ion. Okay. Let's look at the other type, the base. So here they give you HPO42 minus. This is, dibasic phosphate, I guess they call it. ClO4 minus HSO4 minus, that's called the bisulfate ion. And then you're not going to have a conjugate base of a base. You can have a conjugate acid of a base. It's the opposite. So conjugate acid. Okay. So the acid has extra H plus, so add an H plus. So now you got 2 hydrogens, but again, you're adding a plus. So now this is just -1. ClO4 minus, going to add an H. But you're adding a plus and a negative is 0, so now it's neutral. Add an H, so you got H2SO4. Adding a plus and negative is 0, so there you go. So this one here does have a negative, but these 2 at the bottom do not. That's perchloric acid and sulfuric acid are those 2 products. And then that's dihydrogen phosphate ion is the one above. Okay, so that's the idea of conjugates. So try to, practice working on identifying conjugates. Okay. Now, in the second section, what we're going to do is we're going to look at the properties of water. This is really a cool thing about water. So this is section 2. Water is a neat thing. It's a neat compound. What it can do is called autohydrolysis. Hydrolysis means reaction with water. So autohydrolysis means water reacting with itself, water reacting with water. So here's what happens. We can write it this way. It doesn't matter which one you pick. I'm just picking this one. One of the water molecules will react with the other by transferring an H plus to the other one. So when you lose the H plus, you get OH minus. So that would be this one and this one, right? So this one's acting as the acid. We could have had the second one act as an acid. It doesn't matter which one you pick. The first one we're going to say is acting like an acid. That means the second one is acting like the base. So what it's doing is accepting the H plus. So you get H3O plus. By the way, these are aqueous because they're dissolved in water. Ions generally dissolve in water, and these are liquids, most likely. Okay, so what do we have here? Acid. And I want to be careful. I don't want you to misinterpret. This is the base up here, okay? And then this is the conjugate base. Remember, the acid and the conjugate base differ only by an H plus. So H2O and OH minus differ by an H plus. The one with more hydrogens is the acid. The one with fewer is the base. Likewise, this guy changed here too. It accepted an H plus to become hydronium ion, right? Remember, this is called hydroxide. This is called hydronium ion. And make sure you got those terms. Okay, so this is the base, so this is the conjugate acid. I guess I'll write it over here. And that's called autohydrolysis. This happens in room temperature. Water molecules react with each other. However, I'm going to write it this way. I'm just going to say, look, 2 water molecules are reacting, so I'll just combine them like this. So these and these are together. It is a reversible reaction, so you don't get a lot. Remember our equilibrium constant? So let's do Kc. We're going to be in water, so we'll do concentrations. Concentration of hydroxide times concentration of hydronium. And that Kc is such a special K, special K, it's not a cereal. We're going to call it Kw, W for water. Okay, so Kw is a special constant for water. Notice I didn't put any reactants in the denominator. Why didn't I put concentration of H2O squared? It's a liquid. Remember, heterogeneous equilibrium, you don't include solids or liquids. Sometimes, I'm not going to get into the details of this. We're not going to include it here. So notice this is just a product, right? When I say product, that's a double entendre. It's products because they're the 2 products, but it's also 2 things multiplied together. That's a product, a mathematical product, right? And it turns out at 20 degrees C, this value is very small. 1.0 times 10 to the negative 14. That's a crazy small number. Okay. So that's the value you want to memorize. Remember this. 1 times, you don't even have to put the 0.0, just 10 to the minus 14 or 1 times 10 to the minus 14. That's the value. Not very big. And that's probably a reasonable thing, right? If it was large, that would mean that in our bodies, we'd have like huge concentrations of hydroxide and hydronium. In fact, they're very small relatively small concentrations in water. So actually mathematically, what would they be? So, if you did your ice table here, this is a liquid, so we're just going to ignore, right? We don't need to worry about liquids. It's not in the equilibrium expression here. So these start at 0. If they've got to go up, right? K is greater than 0, so we've got to have some products. So this will go up by plus X, this will go up by plus X. At equilibrium, you just have X and X. So this is the hydroxide concentration, which would go here. This is the hydronium concentration, so that would go there. So what you get is Kw is x times x, hydroxide times hydronium. Well, that's just x squared, right? And that's equal to 1 times 10 to the minus 14. So even there, I left the 0.0 out. It does depend on temperature. K gets a little bit larger at higher temperatures, but for the most part, we just use 10 to the minus 14. So that means something. What it means is X is the equilibrium concentration of hydroxide, right? And X is also the equilibrium concentration of hydronium. So what that tells us is that if we just have water, we haven't added any acids or bases, these are equal to each other. So mathematically, here's what happens. If you have x times x, which is x squared, equals 1 times 10 to the minus 14, x is just the square root of that. So that's just 1 times 10 to the minus 7. So at equilibrium, hydronium and hydroxide in pure water is actually going to be x, which is 10 to the minus 7. So we can say that at equilibrium, and at 20 degrees C anyways, pure water has the following concentrations. Hydroxide, 1 times 10 to the minus 7 molar. Hydronium, 1 times 10 to the minus 7 molar. Isn't that cool? They're equal to each other, right? Now, add an acid, it'll become acidic. Add a base, it'll become basic. We'll look at those kinds of solutions later on. But for right now, pure water, those are your concentrations. We'll get the pH and all that as well. So let's look at an example. By the way, this is section 16.2 if you're interested. Interconverting hydronium and hydroxide concentration at 25. I said 20 degrees C. I think it's actually 25, but not a big deal. An aqueous solution at 25 degrees C has a hydroxide concentration of 3.5 times 10 to the negative 8. Ooh, molar, right? Calculate H3O plus concentration. In other words, calculate the hydronium concentration. Be sure your answer has 2 significant digits, okay? So these are very easy. These are very easy problems. You got to get these right. Here's what you do. Concentration of hydronium times concentration of hydroxide is 1 times 10 to the minus 14. In this particular problem, they're telling you the hydroxide concentration. And all they're asking you to do is find the hydronium concentration. Right? That's easy. You know this number, find this number. Well, what we would do is we would divide both sides by hydroxide, and we'd get that the hydronium concentration would just be Kw divided by the concentration of hydroxide. Okay, I'm going to leave the units out there. It is molar, but I'm going to leave it out. Okay. All right, so there we go. So let's see what that is. Remember, you got to know how to use your calculators. So 1 times 10 to the minus 14 over 3.5 times 10 to the minus 8. And you get, ooh, it's a small number, 2 significant digits. So 2.9 times 10 to the minus, I think it's 7. I can actually figure it out. Put molar. Remember, we don't use the units in the calculations that involve K, but then you put the molarity units in at the end. I knew that was minus 7 because minus 14 over minus 8, 10 to the minus 14 over 10 to the minus 8 is 10 to the minus 6. But then 1 over 3.5 is less than 1. So it's going to move it over 1 and it'll be 10 to the minus 7. Okay. You can check your answer. Why? Hydroxide times hydronium is Kw, and we know what Kw is. So if you take this number and you multiply it by this, you should get that number there, taking into account rounding issues, right? Let's take a look at another example. So I've looked at 5 examples. They're all giving you the hydroxide. Here, no, everyone seems to give you the hydroxide. You can go either way. Oh, here's one. Okay. I just had to go through a bunch to get to this one. There we go. Okay. Again, interconverting hydronium and hydroxide at 25 degrees C. An aqueous solution at 25 degrees C has a hydronium concentration of 1.6 times 10 to the minus 6 molar. Calculate the hydroxide concentration and be sure your answer has 2 significant digits. So 1.6 times 10 to the minus 6 molar, that's the hydronium concentration, not the hydroxide, right? So yeah, they could even make it trickier and just give you the names instead of the actual formulas. Okay, now I don't have a good memory. I don't have a good short-term memory. Here we go. So here's what you're given. The hydronium concentration is 1.6 times 10 to the minus 6 molar, and we want to find the hydroxide concentration. Okay, well, here's what we do. Kw is equal to the concentration of these two multiplied together, right? We want to find hydroxide, so divide both sides by hydronium. See, I'm doing it in symbolic form now instead of putting the numbers in. That's generally how I do it. I do the symbols first and then put the numbers in, but you can put the numbers in whenever you feel like it. So Kw is, well, that's the one I said, remember, right? 1 times 10 to the minus 14 divided by 1.6 times 10 to the minus 6. And that should be hydroxide concentration, okay? So 1 times 10 to the minus 14 divided by 1.6 times 10 to the minus 6, and you get 6.25. Well, it actually works out to 6.25. That's sort of interesting. 2, 4, 6, 8. Looks like it's minus 9. That makes sense. That's your hydroxide concentration. They wanted to 2 significant digits. So I think the rule, you can send me an email or contact me if I'm wrong, is that if you're right at 5, there's no digits after it. So let me just make sure. 1 over 1.6, yeah, you get 625. You're kind of stuck how you round it. You either round it up or you round it down, right? If it was 5.1, you would round it up. If it was 4.9, you would round it down. But if it's exactly 5, what do you do? And I believe the rule is if the number right in front of it is even, then you round it up. And if it's odd, then you round it down. So if the 2 is a 3, you would round it down. If the 2 is a 4, you would round it up, even up. Odd down. I think that's the rule. You could look it up on the internet. Let's just Google that. It's not a huge issue, but you don't want to run into this problem. So I think you round it up. So 6.3 times 10 to the minus 9 molar, and that would be your hydroxide concentration. Okay, so a couple basic type skills. This chapter, look at it as skill set. So it's like every class you come, you learn a little algebraic trick, right? This is what we're doing in this chapter. Is section 1, we learned how to write the equation, right? For Bronsted acid base reaction. Now we learned how to interconvert hydronium and hydroxide. So what'll happen is, as we go through this chapter, we'll start doing like pH calculations and then pOH calculations, estimating pH, and then we'll do strong acids and strong bases, then we'll do weak acids and then weak bases, and we'll go forth, and so you start building up. So make sure you practice these early ones first, get good at them, make it second nature, right? Like how to add by 5s. 15 plus 25 is 40. Same thing here. If you're given the hydroxide, calculate the hydronium fast. If you're given the hydronium, find the hydroxide fast. That will help you when you get to the later sections, and mainly the next chapter, when you get to chapter 17, when we're dealing with more complicated solutions like buffers and titration curves. Those skills will come in handy. Okay, take care.